Okay, so a spotlight is on the ground 20 feet away from the wall, and a 6-foot tall person is walking towards the wall at a rate of 2.5 feet per second. How fast is the height of the shadow changing when the person is 8 feet from the wall? Is the shadow increasing or decreasing in height at this time? So first of all, the picture here is kind of helpful, but I just want to make sure that everybody understands it. And I'm going to actually white out. This is the given rate, but it's just written slightly different than what the notation we've used. And we're going to already state our given rate separately. So we have a 6-foot tall person. Here's my 6-foot tall person who's walking towards the wall. Okay. And there's a spotlight back here, and that spotlight is shining on the 6-foot tall person's back. And it goes past his head and creates a shadow on the wall. The distance between the person and the spotlight in this picture is called X. And that distance is going to be increasing as the person is walking towards the wall. If the person were walking away from the wall, then X would be decreasing, but it's increasing as the person is walking towards the wall. Since we are given that the distance between the wall and the spotlight is 20 feet, then we can say that the distance between the wall and the person is 20 minus X. Okay, and 20 minus X is going to be decreasing as time is passing because the person is walking towards the wall. So that distance is getting shorter and shorter. The distance between the spotlight and the actual wall, that's not changing. That's going to stay constant. And then in this picture, the height of the shadow is being referred to as Y. Is everyone okay with this picture and how it's labeled? Do we kind of understand the situation? There's a spotlight behind the guy or the girl, whoever, the 6-foot tall person, and they are walking towards the wall. So their shadow height is going to be changing on the wall based on them getting closer and closer and closer to the wall. Okay, so now we'll go back to our normal steps that we follow for these problems. So we'll state the given rate. So we're given that the 6-foot tall person is walking towards the wall at a rate of 2.5 feet per second. So I don't want to think of that as, sorry, you guys, as 20 minus X changing, because that's just kind of complicated to think of. D of 20 minus X of dt. So I'm going to interpret that as the rate at which X, the distance X, is increasing with respect to time. So we're given that dx over dt is equal to positive 2.5 feet per second. And again, that's positive because as time is passing, we know that that distance X is going to be increasing. We want to find how fast the height of the shadow is changing when the person is 8 feet from the wall. So we want to find how fast y is changing with respect to time. So that's dy over dt. When the distance between the person and the wall is equal to 8 feet. So that would be when 20 minus x is equal to 8. And you could solve for what x would be equal to at that moment just by subtracting by 20 on each side, dividing by -1. You see that x is equal to 12 feet at that moment in time. Or you could have figured it out just thinking you know that the spotlight is 20 feet from the wall. So if the distance of the person to the wall is 8 feet, then that means that the distance from the person to the spotlight would have to be 12. Kind of solve that by inspection. That's also an option. So we've stated the rate that we're given. We've stated the rate we're trying to solve for. We need to come up with the relationship between the quantities that are changing, which are x and y. So going back to the picture, coming up with this relationship is slightly different than the other examples that we've done. And I want to show you guys that there are 2 different right triangles that can be drawn. So there's this smaller right triangle that's created from the person and the spotlight shining. And then there's a right triangle with the wall and the shadow and the spotlight. And those 2 right triangles can actually be thought of as similar right triangles, right? Because this angle here would be equal to this angle here, and then they obviously both share the same angle down here. They both have a right angle. So they're similar right triangles. And if you remember from studying trig or from geometry, the ratios of the sides of similar triangles are equal. So we can come up with a relationship between x and y by coming up with some ratios of the sides of these 2 similar right triangles. So looking at the larger right triangle, if I took side y, which is the height of the shadow, and put it over 20, so the distance of the spotlight to the wall, that ratio would be equal to the height of the person over the distance of the person to the spotlight, x. And this is, again, thinking similar triangles. And if you're thinking, I never would have come up with that on my own, it's only because you haven't done any of these problems before. I told you, we're kind of going through all the different common types of related rates problems. So we can leave the equation the way that it's written. Whenever we would want to differentiate with respect to t, we would have to deal with x to the negative first. I would prefer to kind of, I think it's simpler if we think about multiplying by x on both sides. So we would have x, y equals, and then multiply by 20 on both sides. So equals to 120. But you could differentiate with respect to t either way that relationship is written, that equation is written. Okay, I'm going to pause for a sec. Does anyone have any questions up to here? Okay. So we're ready to differentiate with respect to t. And remember, we have to state that we're doing that first. On the left side, that's x times y, so we need to use product rule in order to differentiate. So first factor times the derivative of the second factor with respect to t is dy over dt, plus the second factor times the derivative of the first with respect to t. Would be equal to 0, since that's the derivative of a constant on the right-hand side. And then kind of the nice part about these problems is after you differentiate, you can usually just look at what you can plug in. So we've come up, by differentiating, we've come up with the relationship between the rates of change, the related rates, and now we can plug in values. So dx over dt is going to be 2.5. We can plug in 12 for x. We're solving for dy over dt, but we need y. So kind of like in the ladder example from the other day, where we had to solve for one of the other measurements or quantities for that particular moment in time that we were solving for the rate of change. We can go back to our original equation, or either one of them, and plug in 12 for x in order to solve for y. Doesn't matter which one, we can use the one that we differentiated, right? So we could do 12 times y equals to 120. So y equals to 10 feet. So plugging those values in, of 12 times dy over dt plus 10 times 2.5 equals to 0. So that's 12 times dy over dt plus 25 equals to 0. Or dy over dt equals to negative 25 twelfths. And for units, since y is measured in feet, right? Feet is what we're measuring distance in for this problem. And time is being measured in seconds, I believe. Yes. The units on dy over dt will be feet per second. And because we got a negative rate, that tells us that as time is passing, y is going to be decreasing. So to summarize, we can say the height of the shadow is decreasing at a rate of 25 twelfths feet per second when the person is 8 feet from the wall.
Are you gonna have us write those on tests, those sentences?
Yes.
Okay.
Well, this won't be, I'm not giving you guys a formal test, but for whatever assignment you do or whatever I end up giving you guys to assess your knowledge on related rates, yes, you do want to summarize with a sentence. And be very careful, whenever you do have a negative rate, make sure that you're interpreting that negative with a word. Like in this case, the decreasing indicates that the rate is negative. How are we doing, you guys? Do we have any questions? I'm going to stop